Here is a question that kept me awake many nights. It is the deepest puzzle I know. Why can you remember yesterday, but not tomorrow? Now wait, that sounds like a trick question. Of course you cannot remember tomorrow. Tomorrow has not happened yet. But here is the strange thing. The laws of physics do not care about the difference between yesterday and tomorrow. If you look at the equations, the ones that describe how particles move and collide, they work perfectly well forwards or backwards in time. There is no arrow painted on them saying this way to the future. And yet here we are, stuck on a one-way train from the past to the future, and we cannot buy a return ticket. By the end of this lecture, you will understand why broken eggs never unbreak. You will understand why ice melts in your drink, but your drink never freezes into ice cubes. And you will understand why, at the deepest level, we know this remains one of the greatest unsolved mysteries in all of physics. The answer involves thermodynamics, probability, and the birth of the universe itself. Let us start with something you see every day. You wake up in the morning and you make yourself a cup of coffee. You put in some cold milk. What happens? The hot coffee and cold milk mix together and you get lukewarm coffee with milk in it. That is perfectly ordinary. Now here is my question. Have you ever seen it go the other way? Have you ever seen lukewarm, milky coffee spontaneously separate into hot black coffee and a floating blob of cold milk? Of course not. That would be crazy. If you saw that happen, you would call a doctor or check for hidden cameras. But here is the puzzle. Every single molecule in that coffee cup is bouncing around according to Newton's laws. And Newton's laws work perfectly well in reverse. If you could take a movie of all those molecules and run it backwards, every collision would still obey Newton's laws. The backwards movie is just as legal, just as permitted by physics, as the forwards movie. So why does it never happen? Why does the milk always mix and never unmix? This was the question that tormented Ludwig Boltzmann in the 1870 seconds. Boltzmann was an Austrian physicist, a big fellow with a bushy beard and an enormous mind. He loved atoms at a time when many scientists did not even believe atoms existed. And he discovered something profound. The answer, Boltzmann said, is not about what is possible. It is about what is probable. Let me give you an analogy. Suppose you have a box with 100 numbered balls in it. 50 are red and 50 are blue. You shake the box. What arrangement do you expect to find? Well, there are fantastically many ways to arrange those balls. Most of those arrangements look pretty similar. A jumbled mess of red and blue scattered throughout the box. But there are very few arrangements where all the red balls happen to be on one side and all the blue balls on the other. So when you shake the box, you are overwhelmingly likely to find a jumbled mixture, simply because there are so many more mixed-up arrangements than sorted ones. It is not that the laws of physics forbid a perfectly sorted arrangement. It is just astronomically unlikely. Now imagine that instead of 100 balls, you have a cup of coffee containing something like 1 trillion molecules. The number of mixed arrangements compared to unmixed arrangements is not just large. It is incomprehensibly, unimaginably, ridiculously large. The ratio is a number with more zeros than there are atoms in the universe. This is entropy. Entropy is a measure of how many different microscopic arrangements correspond to what you can see with your eyes. High entropy means many arrangements. Low entropy means few arrangements. And Boltzmann showed that systems naturally go from low entropy to high entropy, not because physics forces them to, but simply because there are so many more high entropy states to wander into. Think of it like this. If you drop a bottle of perfume in the corner of a room, the perfume molecules will spread out through the whole room. They are not being pushed by any special force. They are just bouncing around randomly. And bouncing around randomly will naturally take them from the concentrated state, where all the perfume is in one corner, to the spread out state, where perfume is everywhere. The concentrated state has low entropy. There are relatively few ways to arrange the molecules, so they all stay in one corner. The spread out state has high entropy. There are vastly many more ways to arrange molecules, so they fill the whole room. So Boltzmann's answer to why time has a direction is this. The past has lower entropy than the future because the universe started in an extraordinarily low entropy state. Things are running downhill from order to disorder, from unlikely to likely. And that downhill slide is what we experience as the passage of time. This is a beautiful answer, but it immediately raises a deeper question. Why did the universe start in such a low entropy state? Let me explain why this is such a hard problem. If you took a movie of the molecules in that coffee cup mixing and you ran the movie backwards, you would see the milk unmix from the coffee. Weird, but every collision would still obey Newton's laws. Now, Boltzmann's reasoning says the backwards movie is incredibly unlikely. Fine, but here is the trick. The same reasoning should also say that the current state is incredibly unlikely to have come from the past. This is called the reversibility paradox, or Loschmidt's paradox, after the fellow who first pointed it out to Boltzmann. If the laws of physics are symmetric in time, then any argument that says entropy should increase toward the future should equally well say that entropy should increase toward the past. But that is obviously wrong. We know entropy was lower in the past. That is the whole point. Boltzmann's answer, and it is still essentially the best answer we have, is that we simply have to accept as a fact that the universe started in an extremely low entropy state. This is sometimes called the past hypothesis. It is not derived from the laws of physics. It is an additional fact about the boundary conditions of the universe, about how things were set up at the beginning. Now this might sound like cheating. We are trying to explain why time has a direction, and our explanation is that things started in a special way. But actually, this is quite deep. What it tells us is that the arrow of time is not built into the fundamental laws. The laws are symmetric. The arrow of time comes from the initial conditions of the universe, from the Big Bang itself. Let me put this another way. Suppose I show you a movie of an egg falling off a table and splattering on the floor. You say, oh, that makes sense. The egg fell, it broke, entropy increased. Now suppose I run the movie backwards and you see broken egg pieces leap up off the floor, reassemble themselves into a perfect egg, and jump back onto the table. You say, that is crazy. That violates the laws of physics. But it does not violate the laws of physics. Every molecule in that backwards movie is doing exactly what Newton's laws permit. What makes it crazy is not the laws. It is the initial conditions. For the egg to unbreak, every molecule would have to be aimed just right, with exactly the right velocity, so they all converge on the table at the same moment. That requires fantastically special initial conditions. Those conditions are not forbidden by physics. They are just absurdly unlikely. Now here's a curious thing I worked on early in my career with my teacher, Johnny Wheeler. We asked ourselves whether electromagnetism itself cares about the direction of time. When a charged particle wiggles, it sends out a light wave. That wave travels outward from the particle into the future. We call this a retarded wave because it comes after the wiggle. But Maxwell's equations, the equations that describe light, have another solution. There is also an advanced wave that travels backward in time, arriving at the particle before it wiggles. Now, in ordinary physics, we throw away the advanced solution. We say it is unphysical. But Wheeler and I asked, what if we take it seriously? We developed what we called the absorber theory. The idea was that maybe the laws of electromagnetism really are symmetric in time. Maybe radiation involves both advanced and retarded waves. And maybe the reason we only see retarded waves is because of how matter is arranged in the universe, because there are lots of absorbers in the future, but not so many specially arranged ones in the past. This theory was beautiful, and it taught me a lot. It led me to think about physics in terms of sums over all possible paths, including paths that go backwards and forwards in time. This eventually became the path integral formulation of quantum mechanics. But the absorber theory itself ran into difficulties. Hans Bethe showed me that certain quantum effects, like the Lamb shift, require particles to interact with their own fields, and our theory did not allow for that. Still, the idea haunted me. Why do we choose the retarded solution and throw away the advanced one? It comes down to the same problem. The universe has different boundary conditions at the beginning than at the end. The past is different from the future, and we put that difference in by hand. Now let me tell you about another arrow of time, the psychological arrow. This is the one you feel directly. You remember eating breakfast this morning. You do not remember eating dinner tonight. Your memories all point toward the past. Why? Here's a way to think about it. A memory is a record. It is some arrangement of neurons or ink on paper or grooves on a record. To create a record, you have to interact with the thing you are recording. Your eyes absorbed light that bounced off your breakfast. That light was emitted by a lamp, which got its energy from electricity, which came from a power plant burning fuel. Every step in this chain produces waste heat. Creating the memory increased the entropy of the universe. Now think about this carefully. The reason you can have memories of the past is that the past had lower entropy. There was free energy available to do the work of making records. The future, as far as you are concerned, is the direction of increasing entropy. So you cannot have memories of it. Memories require the entropy gradient. This is why the psychological arrow, the direction in which you remember things, must point in the same direction as the thermodynamic arrow, the direction in which entropy increases. If your brain somehow ran backwards, with entropy decreasing, your memories would be erased rather than created. You would not experience time running backwards. You would experience nothing at all. Now I want to address a misconception that I have heard people express. Some folks say, but wait, what about those kaons? Do they not violate time symmetry? Yes, there is a tiny effect. In 1964, Cronin and Fitch discovered that certain exotic particles called neutral kaons behave slightly differently when you reverse time. This was shocking. It showed that at the fundamental level, the microscopic laws of physics are not perfectly symmetric under time reversal. But here is the important point. This effect is tiny. It is a fraction of a percent, and it has nothing to do with why ice melts, or why eggs break, or why you remember yesterday. The kaon asymmetry is far too small and far too special to explain the everyday arrow of time. The thermodynamic arrow, the one that governs everything you experience, comes from the statistics of huge numbers of particles and the special initial conditions of the universe, not from some subtle asymmetry in the decay of rare particles. So let us come back to the big question. Why did the universe start in a low entropy state? Some people have tried to explain this with inflation, the idea that the very early universe underwent a period of incredibly rapid expansion. Maybe inflation somehow smoothed things out and produced the low entropy conditions we needed. But this is controversial. Critics argue that inflation itself requires special initial conditions, so you have not really explained anything. You have just pushed the question back one step. Others have proposed that maybe the question is not well posed. Maybe asking why the universe started in a low entropy state is like asking why there is something rather than nothing. It is just the way things are. I find this unsatisfying. If I find a playing card face up on a table, and it is the 7 of hearts, I do not wonder why it is the 7 of hearts rather than some other card. But if I find a brand new deck of cards perfectly sorted in order, I want to know how it got that way. The initial state of the universe was not just any old state. It was an extraordinarily special state, far more special than a sorted deck of cards, that demands explanation. There are more exotic proposals. Maybe our universe is part of a much larger multiverse, and our low entropy beginning is just one of many different beginnings happening in different regions. Maybe our Big Bang was actually a bounce, a moment of minimum entropy between a contracting phase and an expanding phase, and time's arrow points away from the bounce in both directions. These are fascinating ideas, but we have no way to test them yet. Let me give you a thought experiment to drive home how strange all this is. Imagine you are watching a movie of a glass of water with an ice cube in it. You see the ice cube slowly melt. Entropy is increasing. Normal, everyday stuff. Now, I tell you, I am going to reverse the movie. You expect to see the water freeze back into an ice cube? Entropy decreasing? Weird, but understandable. But here is the twist. How do you know which way I was running the movie in the first place? You assume the ice was melting because that is what your experience tells you to expect. But a creature who only knew the laws of physics and had no experience of the world would have no way to pick out one direction as forwards. The laws of physics are like a road that goes both ways. The road does not tell you which way to walk. You need something else, some extra information, to pick out a direction. In our universe, that extra information is the Big Bang. So what have we learned? Time has a direction because the universe started in an extraordinarily special low entropy state near the Big Bang. As the universe evolves, entropy increases, and this increase defines the arrow of time. The laws of physics do not pick out a direction. The initial conditions do. We remember the past and not the future because making memories requires an entropy gradient, and the gradient points from the low entropy past to the high entropy future. The tiny time asymmetry in certain particle decays is real but irrelevant to the everyday arrow of time. And the deepest question of all, why the universe started in such a special state, remains unanswered. It is one of the great mysteries. We do not know if there is an explanation or if we just have to accept it as a brute fact. This is what I love about physics. You start with a simple question, like why can you not remember tomorrow, and you end up at the edge of what we understand about the universe itself. The arrow of time points from the Big Bang toward the heat death of the universe, and every broken egg, every melting ice cube, every memory in your head is carried along by that cosmic current. I have spent a lot of time thinking about these things, and I am not embarrassed to tell you that we do not fully understand them. That is not a failure. That is the frontier. The frontier is where the interesting questions live. If you found this fascinating, leave a comment telling me what other deep questions about time you would like me to explore. Does the thought of a cosmic entropy gradient filling your every memory make you feel small, or does it make you feel connected to something vast? I would love to hear your thoughts.